Imagine this, out of all the possible ways our universe could be, it just so happens to be perfect for life. Coincidence? Or is there something more to it? Back in 1957, physicist Robert Dicke proposed the idea that we can only observe a universe capable of supporting intelligent life. Why? Because, well, we're here to observe it. It's like asking, why do we find ourselves on Earth? Because Earth is the only planet we know of that can sustain life. The anthropic principle comes in two main flavors, weak and strong. The weak anthropic principle, or WAP, suggests that the universe's fine-tuning is the result of selection bias. Think about it this way: if the universe weren't suited for life, we wouldn't be here to notice. Some theories even suggest there's a multiverse out there with countless universes, and we just happen to be in the one that's perfect for us. On the flip side, the strong anthropic principle, or SAP, takes it up a notch. It claims that the universe is somehow compelled to develop conscious, sapient life. One fascinating version of this is the participatory anthropic principle proposed by John Archibald Wheeler. He suggested that the universe, in order to exist, must be observed. So, in a way, we as observers are essential to the universe's very existence. Mind-blowing, right? But wait, there's more. The final anthropic principle, proposed by John and Frank Tipler, goes even further. They argue that the universe's structure can be expressed in bits of information, making information processing inevitable and eternal. It's like saying the universe is destined to produce intelligent life that can process information forever. Let's now delve into the realm of observational evidence, or the lack thereof, pertaining to these fascinating concepts. First, let's address Carter's weak anthropic principle. This principle essentially offers advice to scientists, suggesting that we should take into account the fact that our observations of the universe are conditioned by our existence as observers. Importantly, it doesn't assert anything that can be debated or falsified through observational evidence. It's more about guiding our scientific inquiries. On the other hand, Barrow's strong anthropic principle posits that the universe must have properties that allow life to develop at some stage. Testing this principle directly is a monumental challenge. The most obvious test would be to find evidence of life in universes other than our own. However, by most definitions, any other universe is unobservable. If it were observable, it would simply be considered part of our own universe. Philosopher John Leslie provides an intriguing perspective on this. According to Leslie, if we accept Carter's SAP within the context of a multiverse, we can make several predictions. Physical theories will evolve to support the hypothesis that early phase transitions occur probabilistically rather than deterministically. This would imply that there is no deep physical reason for the values of fundamental constants. Various theories proposing the existence of multiple universes will prove to be robust and gain acceptance in the scientific community. Evidence supporting the notion that our universe is fine-tuned for life will continue to accumulate. We will not discover life forms that do not rely on carbon chemistry. Mathematical studies of galaxy formation will confirm that such formation is highly sensitive to the rate of expansion of the universe. In 1961, physicist Robert Dicke made a striking observation. The age of the universe, as seen by living observers like us, isn't just a random number. Instead, it's fine-tuned by biological factors that place us in a golden age, a period that is neither too young nor too old for life to thrive. Consider this: if the universe were just 1/10 of its current age, there wouldn't have been enough time for stars to produce the heavy elements essential for life, like carbon and oxygen through nuclear synthesis. Small rocky planets, the cradles of life, wouldn't even exist. On the flip side, if the universe were 10 times older, most stars would have already burned out and turned into white dwarfs, apart from the dimmest red dwarfs. Stable planetary systems would have long ceased to exist. Dicke's insights didn't stop there. He also reasoned that the density of matter in the universe must be almost exactly at the critical level needed to prevent a big crunch, a catastrophic collapse of the universe. This observation, known as the Dicke coincidences, aligns with the most recent measurements suggesting that the observed density of baryonic matter and dark matter accounts for about 30% of this critical density. The rest, it seems, is contributed by a mysterious cosmological constant. Speaking of the cosmological constant, Nobel laureate Steven Weinberg gave an anthropic explanation for its remarkably low value. He noted that if this constant were only slightly larger, the universe would experience catastrophic inflation, preventing the formation of stars and consequently life. It's as if the universe's physical constants, like the fine structure constant, are balanced on a knife's edge, perfectly tuned to permit the formation of matter and the emergence of life. Even slight changes in the strengths of the four fundamental interactions, gravity, electromagnetism, and the strong and weak nuclear forces, could drastically alter the universe's age, structure, and capacity for life. For instance, a small increase in the strong interaction could convert all hydrogen in the early universe to helium, making water and long-lived stable stars, both essential for life, impossible. These observations not only deepen our understanding of the anthropic principle, but also highlight the intricate balance that makes our universe just right for life. Imagine a universe where the fundamental constants are slightly different. In this hypothetical scenario, stars might not form, or if they do, they might burn out too quickly to support life. This chapter explores the delicate balance required for a universe to be life-sustaining. Consider the gravitational constant. If it were just a bit stronger, stars would consume their nuclear fuel much faster, leading to shorter lifespans and less stable environments for developing life. On the other hand, if gravity were weaker, stars might not ignite at all, leaving a universe filled with cold, dark matter. Next, think about the fine structure constant, which governs the strength of electromagnetic interactions. A slight increase in this constant would mean that electrons would bind more tightly to nuclei, making it harder for atoms to form molecules. Without molecules, the complex chemistry needed for life would be impossible. Let's not forget the strong nuclear force, which holds protons and neutrons together in atomic nuclei. If this force were just a bit stronger, protons would bind to each other too easily, converting all hydrogen into helium during the early stages of the universe. Without hydrogen, stars like our Sun couldn't exist, and neither could water, a crucial ingredient for life as we know it. The weak nuclear force also plays a pivotal role. It is responsible for processes such as nuclear fusion in stars and radioactive decay. If it were weaker, the Sun's nuclear reactions would proceed too slowly and the universe would be a much colder, darker place. Conversely, if it was stronger, these reactions could occur too rapidly, making stars unstable and short-lived. Even the cosmological constant, which drives the accelerated expansion of the universe, must be finely tuned. A slightly larger value would cause the universe to expand too quickly for galaxies to form, while a smaller value could lead to a big crunch, a catastrophic collapse of the universe. These constants are not just numbers, they are the delicate threads that weave the fabric of our cosmos. Any significant deviation from their current values could render the universe inhospitable to life. This fine-tuning raises profound questions about the nature of our existence and the underlying principles governing the universe. Having explored the delicate balance that makes our universe life-supporting, it's time to reflect on the broader implications of the anthropic principle. This principle suggests that the universe's fundamental constants are not random. They are remarkably fine-tuned to allow for the existence of life, particularly intelligent life capable of pondering these very questions. First, let's recap the key points we've discussed. We've seen how various constants, from the gravitational constant to the fine structure constant, play pivotal roles in making the universe hospitable. Even slight deviations from their current values could lead to a cosmos where life, as we know it, would be impossible. But what does this mean for our understanding of the universe and our place within it? The anthropic principle forces us to consider the possibility that the universe is not merely a random occurrence, but has properties that are remarkably conducive to life. This raises profound questions about the nature of reality and our role in it. Philosophically, the anthropic principle has sparked intense debates. Some argue that it hints at a purposeful design, while others see it as a natural consequence of the vast number of universes in a multiverse scenario. In this view, we just happen to be in one of the rare universes where the conditions are right for life. Scientifically, the anthropic principle challenges us to delve deeper into the laws of physics and the origins of these constants. Are they truly fundamental, or are they the result of deeper, underlying principles that we have yet to discover? The quest to answer these questions drives much of modern cosmology and theoretical physics. Looking to the future, the anthropic principle will continue to influence our exploration of the cosmos. As we develop more advanced technologies and methodologies, we may uncover new insights that reshape our understanding of life and the universe. Perhaps we will discover other life-supporting worlds or even entirely new forms of life, further enriching our perspective on the anthropic principle. In conclusion, the anthropic principle is more than just a scientific concept. It is a lens through which we view our existence and the universe.